All right, you've reached your last lesson, lesson 7 for chapter 3, powers and exponents. We are going to look at some common types of problem-solving questions you will see that involve exponents. So we will begin. We're going to be checking a lot of these in class together, so if they don't really make sense at first, then hopefully tomorrow in class we can discuss them and they'll make a bit more sense for you. A little side note, I have just done all of your lessons back to back, and so because this is the last lesson, just like lesson 8 last time, keep a close eye. I'm going to try not to make any mistakes. I think everything's good, but if you see anything, make sure you let me know, or if something doesn't seem right, we'll talk about it tomorrow. Okay, so our first example says, we have a blue square inside of a green square. The blue square has side lengths of 5 centimeters. Now, keep in mind, if I'm telling you it is a square, all the side lengths are equal. So 5 by 5 by 5 by 5. And again, I'm not sure why on the smartboard it's looking more rectangle than square. But hopefully on your printout it looks more square to you. So anyways, a blue square with side lengths of 5 centimeters is placed onto a green square. So again, we have a square with side lengths of 9 centimeters. So 9 by 9 by 9 by 9. We want an expression with powers that determines the visible green area. So basically, we started with a green square. Okay, we had a bigger green area, and then we put on a smaller blue area, and so we're going to have less green area left. So I hope you notice that this is a subtraction question. So we have a green area squared. The green side lengths are 9, so we're going to have 9 centimeters squared, and we're going to take away the blue area that's now covered up the green area, and that is going to be 5 centimeters squared. I want you to think about why I put 9 centimeters and 5 centimeters inside brackets. What does that mean when we put a base inside brackets? Well, when we put a base inside brackets, it means the exponent applies to everything. So we get 81, so the 9 has been squared, and also the centimeters have been squared. Same thing on the 5. The 5 has been squared to 25, and the centimeters have been squared. So this is where we get our area units from. Okay, so we found the expression. So this was our expression involving powers, and then it said, what is the visible green area? So we're going to take 81, subtract 25, and we get 56 centimeters squared that is still visible. So it's the leftover after we've cut out or covered up that area with the green. So you're going to see these type of questions a lot where area gets covered up or maybe pieces get cut out. Very common scenario that you would see. A square inside another square, and we cut out a piece of the area. The square might be in the middle, like in a picture frame or something like that, but a square with a square, really common problem. You'll see these all the time. Less common is a cube inside a cube or subtracting a cube, but you would see that as well. And that would be similar to the example we did at the end of lesson 6. Okay, Mr. Burns, yeah, good old Mr. Burns, attempted to answer a question from Homer's test and thinks he did very well. However, he has made several errors. So on a question like this, when it says, here is somebody's work, I want you to fix it, I think the best idea for you is to rewrite the question and try solving it on your own, and then go back and compare. Quite often, if you just look at their work and then solve it, you will actually make the same mistakes that they have done. So the best thing to do is kind of cover up their work, write out the question for yourself, and try solving. So 2 times 3 squared minus 2 cubed times 2 squared minus 5 to the power of 0. Okay, so I'm going to cover up their work and I'm going to solve it for myself. Okay, we've covered it up. We're going to solve it on our own. And so first thing we do, okay, we're thinking bed mass. We've got some multiplying. We've got some exponents. So we're going to evaluate our exponents first. So 3 to the power of 2, so that's the same as 2 times 9 minus, well, I could evaluate the exponents here, but I also notice that it's the same base being multiplied. So I could go 2 to the power of 3 and write 8, and 2 to the power of 2 and write 4, or I could notice that it's the same base being multiplied, and I'm going to add the exponents. So that's going to be 2 to the power of 5 minus 5 to the power of 0. Well, anything to the power of 0 has a value of 1. Okay, still not quite done. 2 to the power of 5, I'm going to get a value of 32. Let me double check. Yeah, 32. So we have 2 times 9 minus 32 minus 1. Okay, exponents are gone. Now I have some multiplication and I have some subtraction. So we're going to multiply first, and we get 18, take away 32, take away 1. Now it's all subtraction, so I'm going to go from left to right. So I have 18, I'm taking away 32, I'm going to be in the negatives, and then I'm going to take away 1 more, and so I'm going to go 1 more negative, and we end up at negative 15, which is a little bit different than what they got. So they got a negative 28. So what I would like you to do is identify for yourself, where did they make their errors, and what were those errors? Like maybe they used the wrong, they used product of powers when they should have used power of a power, or product of powers, and whatever. Okay, maybe they got the wrong exponent law, or maybe they did something out of order, or maybe they, whatever it is, identify it and then say what it is that they did wrong. We're going to double check what you come up with in class tomorrow. Again, really common type of example you will see. Okay, what is the surface area? Oh, your favorite. I know you love surface area so much. That's why I gave you this example. So it says, what is the surface area of a cube? So we know that all the side lengths are the same because it's a cube. Everything is 5 centimeters, or meters, pardon me. So a cube of an edge length of 5 meters. Okay, well, surface area is area of each face added up. In a cube, we know that there are 6 faces because a dice goes from numbers 1 to 6, so there are 6 faces. And each face, because it is a cube, will have the same measurement. So we're going to go 6 times length times width. But we know that on a cube, each face is a square, so technically each side length is the same. So it's going to be length times length, or width times width, or height times height. And so we can write this as surface area equals 6 times length squared. Or we might just see it as 6 length squared, or 6 width squared, or 6 height squared, whatever. We know that our length is 5 meters, so the surface area is going to be 6 times 5 meters squared. Again, we're putting the whole thing in brackets because the 5 gets squared as well as the m meters. So 6 times 25 meters squared, or 150 meters squared. Hopefully that's a nice review question for you from grade 8. Okay, another example where you have shape inside of shape, and something is being cut out or something is being covered up, and we only want to know part of the area, and we need to know the area of both. So in order to deal with something like this, it says a circle is inscribed in a square. That means a circle is inside the square. And the square has side lengths of 20 centimeters. So remember, it's a square, so that side is 20, and this side is 20. When it's inscribed, what it's saying is the circle goes from one edge of the square to the other. So the diameter of the circle is also 20 centimeters. And then the radius, so remember the radius goes from the center of the circle just to one edge is going to be 10 centimeters. It's half of our diameter. And so we want to know what is the area of the shaded region. So basically we had a square piece of paper, we cut out a circle, we want to know how much of the square paper area is left because the square was bigger. So this is a difference type question, so this is a subtraction type question. So we have area of a square, and we're going to take away area of a circle, and we want to know what's left. So area of a square, we know is side length squared. So we're going to go length squared. And then we're going to be taking away the area of a circle. And look at that. Miss provided us the formula for area of a circle. I'm too nice. So pi times radius squared is going to be subtracted. And I'm going to put it in brackets to show that that whole value gets subtracted. Okay? And so the length of our square is 20 centimeters. So 20 centimeters squared, take away pi. You can use 3.14, but you should be using the pi button on your scientific calculator. That is going to give you a more exact value. So I'm going to write 3.14 in here just for our example, but when you calculate, you should be using your pi button. And the radius we said is 10 centimeters, and that's going to be squared. So we actually have two sets of brackets there, but that's okay. We'll make these ones square to show that they're the outside ones. Okay, so we go 20 centimeters squared. So we get 400 centimeters squared. Take away, well, 10 squared is 100. So this is like saying 100 centimeters squared times pi. And so we get 400 centimeters squared, take away 314.159 centimeters squared, right? Pi is irrational, and so that decimal is going to go on forever. And so when we find the difference of these two values, we get a leftover 85.84 blah, 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 centimeters squared. And so the question doesn't ask us or tell us any decimal places, and so we're just going to take it to one decimal place for now. Okay. Second last example, we have a Pythagorean relationship. And so remembering that for a Pythagorean triangle, we need to be dealing with a right angle triangle, meaning we have a 90-degree angle. And we need to label different parts of this triangle because it says the hypotenuse. So where we find the hypotenuse is we shoot our arrow through the 90-degree angle, and it points to the hypotenuse for us. So that side length is the hypotenuse. And we want to know the area of the square attached to the hypotenuse. Well, Pythagorean theorem tells us that if we take the smaller square for leg A plus the square attached to side B, and we add them, we are going to get this square attached to the hypotenuse, or C. Okay, and so that's what we're going to do. We're going to find out what that area is. So 5 centimeters squared plus 12 centimeters squared gives us the square attached to the hypotenuse. Following our order of operations, we are going to make sure we follow our exponents before we add. Many of you last year in grade 8 would add the 5 and the 12 and then square it, not following your order of operations. This year you are much wiser, so we're going to do 25 centimeters squared plus 144 centimeters squared, and you found those values on your cheat sheet. You didn't even need your calculator. And when we add them, we get 169 centimeters squared as the area of the hypotenuse square. Now let's say I want to know what length is the hypotenuse. Okay, well, the way that we undo a square is we square root. Find the side length of a square, we square root the area. So when we go square root 169 centimeters squared, we get a length of 13 centimeters. So the square of the hypotenuse is 13 centimeters by 13 centimeters. Again, really common type of question. Okay, the last type of question we have is an exponential growth type of question. So bacteria grow exponentially. So unlike when you were made and you needed your mommy and your daddy and a whole lot of love in the room and a little bit of God, bacteria just need themselves. And so bacteria like to reproduce by splitting. So one bacteria becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, 16 becomes 32, etc., etc., etc. So every time they double in number. So we call this exponential growth because it's doubling every time. It's speeding up. The more you have at one instance, when the next split happens, you're going to have double that amount. So it's getting larger and larger exponentially. And so the most common type of questions you see do involve bacteria. And so this type of bacteria, we start with 100 bacteria in a dish. So at time 0 hours, the number of bacteria in the dish is 100. I think for you guys, for most of you, it will be most easiest to solve these problems by making a data table. Okay? And so the bacteria doubles in number every hour. So that means after 1 hour, we are now going to have 100 times 2. So after 1 hour, there will now be 200 bacteria. We want to know how many will be present after 1 hour. Okay, well, we have that. 3 hours and 7 hours. So we're going to keep going. We're going to go 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, 7 hours. Table's just going to have to come off to the side. So we're going to keep doubling it. 200, 400, 800, 1,600, 3,200, 6,400, 12,800. So after 1 hour, there will be 200. After 3 hours, there will be 800 bacteria. And after 7 hours, there will be 12,800 bacteria. So you can see how quickly it starts to grow in exponential growth. My challenge to you is I want you to find a way to write an expression to solve this kind of question. What kind of expression would we use to represent exponential growth? If you do a little bit of investigating in your textbook, you can find it, or you might have had some exposure to this already through your science. We're going to talk about what that would look like tomorrow, but a table always works. So this is it for chapter 3. The next thing you will be expecting is your formal and then your chapter test.